So, are you expecting any more? No idea. Yeah, heavily raining. All right, guys, then we'll start. Okay, in the last class, we'll just go through what we have done in the last session. Guys, you can hear clear me, right? Chiang? So the voice is clear, right? Oh, all right, Shafruddin. Okay. So we know that basically vibration is a type of motion which repeats itself at fixed intervals of time or at given intervals of time. So when we study mechanical vibrations of a system, so the first thing we do is we need to come out with the equation of motion of the system. So we need to derive the equation of motion of the given system. Can you see clearly? It's getting blurred. All right. Okay, so we need to derive the equation of motion for the given system. So this can be done in two ways. One is using Newton's method. So where we write the sum of the forces acting on the system, we equate with mass times acceleration. So we'll see what are the forces acting along X, along Y, and accordingly, we apply the Newton's method. So if the system is having a rotational motion, then we apply the net torque acting on the system, okay, is equivalent to the moments. Then the other method is the energy method. Okay, so we can use the Newton's method or energy method to derive the equation of motion of a system. Okay, so when we are using the equation Newton's method, so the net force acting on the system, we write it as mx double dot. Okay, so the same thing, if the motion involves rotation, then the net torque acting on the system, we can write it as the mass moment of inertia of the system, I, multiplied by the angular acceleration, theta double dot. Okay, so we can apply one of this method. Okay, so the energy method is the total energy. So we can write the kinetic energy plus potential energy. Okay, so then we need to take the derivative of the total energy with respect to time. Okay, so T plus V, we equate with 0. All right, so when we simplify, take the derivative of the total energy with respect to time, and then simplify, we'll get the equation of motion of the system. So once we know the equation of motion of the system, then we need to study the response of the system. Okay, so we need to study the response of the system. So response of the system refers to how the displacement of the system varies with respect to time. Okay, so how the relationship of the system with respect to the given components. Okay, so we have seen that in the case of harmonic motion. So for harmonic motion, we can write simply the displacement x as a function of time t. Okay, so we can choose as a sine omega t. So omega is the circular frequency, t is the time, and omega t refers to the theta, angular displacement. Okay, so omega t is nothing but theta, which is angular displacement. So we know the derivative of this is the velocity. So we can write the velocity is also a function of time t. So we can write the velocity as omega a into cos omega t. Okay, so we can also write this in terms of sine as omega A sine omega t plus pi by 2. Pi by 2 is the phase. Okay, so we can also write in terms of sine angle also. Then if you take the derivative of velocity, okay, we get acceleration. So acceleration is the second derivative of displacement. Okay, so this one we can write it as negative omega square A sine omega t. Okay, so we can also write this as negative omega square. So A sine omega t we can also replace with xt, the displacement. Okay, so this is basically related to the harmonic motion. Then when we talk about the vibrations, so we can study the vibrations in different ways. So we know that vibrations can be free vibrations. So this is the broad classification, and forced vibrations. Okay, so free vibrations means there is no external force. Okay, again these free vibrations, okay, we can write damped free vibration. So damped free, okay, and damped vibrations. So that means without damper and with damper. So similarly, when we study the forced vibrations, so similarly forced vibrations also we can say that okay, so damped free forced vibrations and damped and forced vibrations. So with damper, without damper. Okay, so broadly we can categorize vibrations as free and forced vibrations. And free vibrations we can in turn classify as the vibrations with only mass and spring system. So no damping. Okay, and we can introduce damper and we can study the system as vibrations with damped, with a damper. So that means we'll have m mass, spring constant, and c the damping constant. So we discussed these aspects in the last class. So similarly, the force vibrations we just repeat with only mass and spring, but there is an external force acting on the system. And the second category, the mass, stiffness constant, the damping constant will be there, and also there is an external force acting on the system. Okay, so when we, in the last session, we looked into, I'll just rewind what we have done. So for free vibrations, free undamped means without damper.
So are you recording the
Second?
Are you recording the class?
No. So free undamped vibration. You want me to record this? Any request for recording? All right. So I'll start recording this session. Okay. So in the case of free undamped vibration, so this refers to mass and spring system. So we have only M and K. There is no damper. So in this case, the equation of motion we can simply write as mx double dot plus k x is equal to 0. So this is the equation of motion of the system. Okay, so the same thing if you are You can also write m I theta double dot. Okay, so k theta is equal to 0. So where your theta is angular displacement. Okay, x is the linear displacement and theta is the angular displacement. All right. So for free undamped vibrations, so we can see that the natural frequency of the system we can relate to the spring constant and the mass. So this is the natural frequency of the system. Okay, so the general solution or the response so we can write it as x is equal to so a constant c sine omega n t plus phi. So this is how the the displacement of the system x varies with respect to time. So where c is a constant, we can also write this response x as, so by taking both cosine and sine term, so we can write a sine omega n t plus b cos omega n t. So where this c can be written as square root of a square plus b square. So a and b are again two different constants. So we can solve a and b by applying the initial conditions. Okay, so for a system vibrating with so under the influence of gravity, so we can write the natural frequency as, okay, square root of g over m. Sorry, so this is square root of g over static deflection. So g over static deflection. All right, so this is for a free undamped vibration. So in the last session, we have considered the damped vibration, damped free vibration. So in the case of damped free vibration, so we have mass, stiffness constant, and the damping constant C. So we study about these three things. So for the damped free vibration, we can write the equation of motion as so here we have my double dot. So where y double dot is the acceleration plus c y dot. So y dot is the velocity. Okay. So plus ky is equal to 0. So this will be the general equation of motion for a damped free vibration. So that means we have the damper, but there is no external force. Okay, so for this, the general solution or the response of the system, we can write in different ways. So we can write the displacement x as a function of time t. Okay, as the maximum amplitude x. Okay, then you can write exponential power minus eta omega n t into sine omega dt, where omega d is the damped natural frequency, plus phi. So we can write the response like this. So we can also write the response in slightly a different form. So I'll just show you. So we can write it both including cosine and sine terms. So the maximum amplitude x multiplied by exponential power eta. So eta is the damping ratio. Okay. So omega n t. Then we can write a cos omega dt plus, okay, another constant b sine omega dt. So we can also write the response of a damp-free vibration like this. So where eta is your damping ratio. Okay, so eta is the damping ratio. So what is damping ratio? The C damping constant over the critical damping constant. Okay, then the omega d is the damped natural frequency. So we can write damped natural frequency as omega n into square root of 1 minus eta square. Okay, so this is for the damped free vibration. So we just touched upon the equation of motion, then the response of the system. So the response of the system, now you can see that there is x, which is the amplitude of the response. So amplitude refers to the maximum displacement. Okay. Then eta is the damping ratio. Okay, C over Cc. Omega n is the natural frequency. Omega d is the damped frequency, or we call it as damped natural frequency. So phi is the phase of the system. Okay, so in the last session we have seen that depending on the damping ratio, okay, so if the damping ratio is greater than 1, implies, if the damping ratio is greater than 1, it implies the system is over damped. I think it is. Okay, so the system is overdamped. Then eta is equals to 1. So we can say the system is critically damped. And if the damping ratio is less than 1, okay, the system is under damped. Means we can expect the system to have some vibrations. Okay, now experimentally, we can study the response of the system, okay, by measuring the amplitudes. Okay, so by measuring the amplitudes. So we define the ratio of two successive amplitudes and natural logarithm of it. So we can say that ln xi over xi plus 1. Simply, we can write it as ln x1 over x2. So we call this as logarithmic decrement. So that means if we know the response of a system, okay, having the damp-free system, M, K, and C, we can measure the response of the system by measuring the amplitudes, how the vibration amplitude varies. Okay, so two successive ratios, that is x1 over x2, then you take the natural log of it, then we call that as logarithmic decrement delta. So basically logarithmic decrement delta, we can write it as natural log x1 over x2. Sometimes we also write this as log x base e. Okay, so if you don't write base e here, it implies base 10. Okay, so if sometimes we can also write like this. Okay, so ln or log to the base e, both are same. So this logarithmic decrement is related to damping ratio. Okay, so we can say that the logarithmic decrement delta is logarithmic decrement. We can find out experimentally by, if you have a system, measure how the system vibration varies. Okay, and take the amplitude of two successive vibrations, then take the ratio, take the natural logarithm of it. So that is logarithmic decrement. So this logarithmic decrement, you can write it as 2 pi eta over 1 minus eta square under root. Okay, so generally I want everybody to scribble out so that you feel some ease in writing the equations. Okay, so one time writing is equivalent to 5 times reading. All right, so here this is how the logarithmic decrement is related to the damping ratio eta. But we can simplify this expression when eta is small. So when eta is small, so you can simply write delta is equal to 2 pi eta, because square root of 1 minus eta square is very close to 1. So when eta is small, we can just write the logarithmic decrement delta as 2 pi into eta. All right, so all these things were done in the last session. So now we know eta is C over Cc, where Cc is critical damping constant. So we can write this as, we can relate this to square root of m into k. All right. So for damp-free vibration, so I just write the response as x, which is a function of time t. So we can write the response xt as x. I just rewriting. So minus eta omega nt sine omega d, the damped frequency, plus phi. So this is the response of the damped free vibration. So guys, take the derivative of this, then you will get the velocity. Okay, so the velocity of the damped free response v is equal to x dot t. Okay, so please find out and let me know. Take the derivative of the above equation and write the response, the velocity. So you need to apply the product rule here. So there are two terms, okay? X is a constant, of course, exponential power, then sine function. So these two are coming as product. So therefore you need to apply the product rule for differentiation. So product rule means differentiation of d by dt of u v is equal to, so u dv by dt plus v du by dt. So you need to apply the product rule here. Guys, online you may try. I'll give you a few minutes for you to work on this. So this term you get when you take the derivative of the first term, exponential term. So exponential power x is equal to exponential power x, but here we have a negative eta omega n t. So negative eta omega n will come into as the multiplication, then x as it is, then the whole thing exponential power. So the next part we need to take the derivative for the sine term. So when you do for the sine term, so sine term will transform to cos. So sine omega d into t, so omega will come. So you have omega d, then exponential power minus eta omega n t, then sine becomes cosine. So this is the velocity for the expression. So if you take the derivative again, then you will get the acceleration response for the damped free vibration. Okay, so the velocity v becomes the whole stuff. All right, guys, any questions? So far what we have done is we have just revised what we have done in the last two sessions. Derivations so will not be asked. So you may have to apply these equations if the person asks you to calculate the velocities. All right. Okay. So with this background, then I move on to the next topic. So the next topic is on forced vibrations. So now we introduce the force component into the vibration. So that is okay. Guys, you need to bear with the slides. The slides may be a bit messy. Why? Because I do not want to introduce you new symbols, okay? Because if you refer some other books or some other slides, the symbols may be changing. So I'm just using your learning material. So whatever I'm presenting you, everything is the same from your learning guide, okay? So now let us move to the next topic, that is forced vibration. Again, we are going to study this forced vibration as two. So the first one is undamped forced vibration. So that means we don't introduce the damper. Okay. So now let us look at this. Okay. So now focus on this system. Okay, so here we are introducing a force component. Okay, so the system is acted upon by additional external force F, and this force is also a periodic force. It is not a fixed force, but it is a periodic force. So when we write the force F is equal to F naught sine omega t. Okay, so guys, can you tell me what is this omega? So anyone, what is this omega? Anyone? Omega is? No, it is angular velocity in the sense that's correct, but here, so this is the frequency at which the force is acting. So this is the harmonic frequency of the force. So you can also write simply as external frequency. So or frequency of the force. Okay, so omega n is the natural frequency of the system. Okay, so when we write omega n is the natural frequency of the system. Now look here, okay, so the vibrating force is given as a periodic force. Okay, so the force is a periodic force, means the force varies with respect to time. So can someone tell me what is F naught? So what is this F naught? So this F naught is the maximum magnitude. So this is the force, maximum force. And when theta is equal to 0, the force is maximum. So when omega t is equal to, okay, 90 degrees, pi by 2. So sine 90 is 1, right? So when omega t is pi by 2, the force F becomes F naught. So the amplitude of the force is F naught. So the F naught occurs when theta is 90 degrees. So the force varies. When omega t is 0, the force is, so sine 0 is 0, right? So the force is 0. So that means the force varies from negative amplitude F naught to positive amplitude F naught. So it vibrates just like the oscillation. So the system. So it's a periodic force with amplitude F naught. Okay. And the frequency of the external force is omega. All right. So now let us derive the equation of motion for this. So we can write the net force acting on the system. So we have only uh, spring force, the inertia force due to mass, and the external force. Okay. So you can write the net force acting on the system, F net is equal to mass into acceleration. Okay. So mass into acceleration, here the motion is in the y direction. So acceleration is y double dot. So you can write y m into y double dot. So what is the net force acting on this system here? Okay. So external force is F naught sine omega t, and the spring force is in the opposite way. Okay. So which is k into y. So this is the spring force. So the net force my double dot is equal to F naught sine omega t minus ky. So the force, downward force is positive, upward force is negative. So we can write simply the Newton's equation. The net force is mass times acceleration. So mass times y double dot. So what is the net force? So the downward force is positive, F naught sine omega t. The spring force is negative. So the total net force is F naught sine omega t minus ky. So now we can rearrange the term. So bring the ky to the other side. So this is the equation of motion. So now you can dividing each term with the m. So this equation can be modified like this. Okay. So finally, the equation of motion, I just clear all this. So the equation of motion, you can write it as y double dash plus k by m into y is equal to f naught over m into sine omega t. So this equation is a non-homogeneous linear differential equation. Why it is non-homogeneous? Because the right-hand side is not zero. So when we dealt with a damped free vibration, then we have only the whole term f naught over m sine omega t is zero. So since we are dealing with a forced vibration, the right-hand side is not zero. So therefore, we consider this as a non-homogeneous second order a linear differential equation. Okay, so we are again dealing with a differential equation because, so you can see here this is y double dot. So y double dot means the second order derivative. So we need to now study the response of this system. Okay, so we have studied the response of the system when this was zero, right? We studied the response of the system the first session. I showed you at the beginning of the session. So when my equation of motion, the right-hand side is zero, that is a undamped vibration, free vibration. Okay, so now we have the right-hand side is no longer zero. So therefore, we are dealing with a non-homogeneous differential equation. Now to solve this equation, okay, there will be two types of solutions we discussed in the very first class. Okay, there will be two solutions. One is the complementary solution, YC. So the other one is the particular solution, YP. Okay, so we already know the complementary solution by considering the right-hand side as zero. So by considering the right-hand side 0, so we know the complementary solution can be written in different ways, and this is one of the way. And we know also that the natural frequency of the system is square root of k by m. So all these things were done earlier. So now we need to find out the particular solution for this. Why particular solution? Because the right-hand side is no longer 0. So now we start considering, now we let the particular solution as c, a constant c, multiplied by the sine function, sine omega t. So now to solve this, you need to write what is the first derivative, yp dot. Okay, then you need to write down what is the second derivative, yp double dot. Okay, if yp is c sine omega t, yp dash will be c omega cos omega t. Then what will be the second derivative? So the second derivative will be negative c omega square, then sine omega t. Okay, so we let yp, the particular solution, as c, a constant multiplied by sine omega t. Then we take the first derivative, then second derivative. Now substitute these values into the equation here. Okay, so the first one is y double dot. So y double dot is negative c omega square into sine omega t. Okay, so plus you need to see the previous equation, k by m into y. So y is c sine omega t. So this is k by m into y. So instead of y, we are writing c sine omega t. Now this is equivalent to f naught over m into sine omega t. So basically we are just substituting the values for y double dot and y in this equation. Okay, so then you will get this expression. Okay, so by substituting back the particular solution into the differential equation, so we'll be getting this. Okay, negative c omega square sine omega t plus k by m. Okay, so now from this, okay, you can simplify it by taking out sine omega t in all the terms. You can take out sine omega t. Then we are writing c as f naught over m. Okay, then you can take here k by m minus c omega square as the factor. So c becomes f naught over m over k by m minus omega square. Okay, so this is just simplifying from here. We can write c. Okay, so now we can further simplify this. Okay, k by m is nothing but omega square is equal to k by m. So you know omega is square root of k by m, right? So we know natural frequency omega n is equal to square root of k by m. So we can write the square of natural frequency is k by m. So we replace k by m with omega n square. Then we'll have omega n square minus omega square. So that one we can further simplify and we can write in this form. Okay, so basically by doing all these things, so what is that we have done? We have taken the particular solution for the differential equation as c into sine omega t. Okay, so we could find out the value of the constant c. So the c can be written as f naught over k over 1 minus omega over omega n square. Okay, so let we study this as omega over omega n is the ratio of, what is omega? This is the external force frequency. Omega n is the natural frequency. So you can call this as R. So R is the ratio of the force frequency over natural frequency, omega over omega n. So in such a case, you can simply write this as F naught over K, okay, over 1 minus R squared simply. Where R, we are going to define R as the ratio of the frequency, external frequency over natural frequency. So what is the unit for R? Guys, anyone, what is the unit for R? Anyone unit for R? R is a dimensionless number, just no units, because it is the ratio of two frequencies. So therefore, R just becomes a dimensionless number, just magnitude. That's correct, Richard. All right. So now, what is that we have done so far? So we got the equation of motion for the forced undamped vibration, undamped force vibration. Now from the equation of motion, we know that the right hand side is no longer zero. So therefore the equation will have two types of solutions. One is the complementary solution. The other one is the particular solution. A complementary solution we already know. So from the previous analysis, we know the complementary solution is A sine omega nt plus B cos omega nt. So we can write the complementary solution like this. Then to find out the particular solution, we choose particular solution in the form as a constant multiplied by sine omega t. And then by substituting the first derivative, second derivative values in the given equation of motion, then you will be able to find out the C value. So that means now we know the complete solution or the complete response of the forced vibration. All right. So now we can write Yp. So Yp is C into sine omega t. So therefore we can write Yp like this. Okay. So Yp, the particular solution for the damped free vibration, can be written like this. Now what will be the complete solution for this? So Y is now the two components we add up. So the complementary solution plus the particular solution. So therefore this response for the damped free vibration becomes like this. So you can see the complete response Y can be written as A sine omega nt plus B cos omega nt. So which is the complementary part of the solution. Then plus you have F naught over K over 1 minus R square. So this is the into sine omega t. So this is the particular part of the solution. So now we can see two solutions. Okay. Now the natural frequency, the complementary solution YC. So it defines the free vibration when there is no external force. Okay. So YC represents the response for the free vibration. So here the natural frequency is square root of K by M. Now Yp, which is the particular solution. Okay. So this Yp describes how the response based on the applied force. Okay. So the response, this part represents the response due to the applied force. Okay, so the first one is the response for the free vibration. The second one is the response for the forced vibration. Okay, so this is how the force is varying the particular, okay, the particular part of the solution varies with respect to time. Okay, so you need to appreciate, I just clear this. So the important part from damped free vibration, that it has two parts of the solution. So the first part is the complementary solution, that is for the free vibration. Okay, the second part is the response due to the force vibration, due to external force. So F naught is the magnitude of the force. Omega here is the force frequency. Okay, so you don't get confused. Now we are dealing with omega. This is always the external frequency, the force frequency. Omega n is the natural frequency. Then omega d is the damped natural frequency. Okay, so generally we define this, combine these things and define the ratio R as omega over omega n. Okay, so this R will be introduced after, I think, one or two slides later. Guys, any questions on this so far? Yes, Azhar or Shashivendran or Jakaria. I didn't get the name. You guys know? Hello? All right. Okay, Daryl. Then we move on to an example now. So we try to look an example related to the damped vibration with external force acting on this. Okay. So now, guys, go through example, read the example, then try to understand what is given there. Okay. So here there is an instrument here. Okay, so this is rigidly attached to a platform P. Okay, which in turn is supported by 4 springs. So there is a mass and there is a spring. So the spring constant, each spring constant is given 800 Newton per meter. So there are 4 springs. So initially the platform is at rest when the floor is subjected to a displacement delta, so which is given as 10 sine 80 mm. Mm is basically the unit for measurement, okay, because delta is the displacement. So we measure displacement in mm. But what is this 10? And what is this 8? Anyone, what is 10 and what is 8? Yes? Which one is frequency? No. Online guys, let me know what is 10 and what is 8. Anyone? 10 is magnitude, that's correct. Correct, Michael. What is 8? So 8 is the frequency of the displacement. So 8 is your omega. All right. So this is the instrument is constrained to move vertically, and the total mass of the instrument and platform is given. So the mass m is given. So you know the spring constant is one spring constant is 800 Newton per meter. So there are 4 springs. So you know the total stiffness and you know the mass. So you are basically dealing with, there's no damper here. Okay, so we are dealing with a damped vibration. But it is not a free vibration, but it is a forced vibration because the floor is subjected to a displacement which is a harmonic function. The displacement is also varying with respect to time. So we can treat this as the force associated. Okay. So now in this case, determine the vertical displacement y of the platform measured from the equilibrium position. So that means y represents the response of the system. So we need to find out what is the response of the system under these conditions. Then what floor vibration is required to cause resonance? So guys, any idea what is resonance? So what is resonance? Any idea? Anyone can tell me what is resonance? No, it's not critical frequency. Any other answers?
Undamped force.
Hmm?
Undamped.
May I know your name, please? I know these 3 people's name. Your name?
Takashi.
Takashi. Oh, earlier this is your first class, right? You didn't attend the first 2 sessions? You did attend online? You didn't attend, right? Yeah, because I remember I was marking at the attendance. It's okay. You're able to cope up? Okay. All right. So, guys, what is resonance? Anyone? What is affected, Shafruddin? No idea? No? Zakaria, no? Okay, there are 2 frequencies. Frequency where the vibration amplify. That's correct, but that's correct, Richeng, but I need a clearer. Okay, so there are 2 frequencies here. Omega is let us say, the frequency of the force. And when this frequency of the force equals to the natural frequency, okay, so what happens? The 2 frequencies matches. So when the 2 frequencies matches, the amplitude of the vibration increases maximum. The amplitude of the vibration becomes maximized. So this scenario is called resonance. So resonance means when the force frequency equals to the natural frequency of the system. In other words, under resonance, R is equal to 1. So that means the ratio of omega over omega n is equal to 1. So simply in resonance conditions means the external frequency equals to the natural frequency of the system. So what? So when resonance conditions happens, when the 2 frequencies matches, the system vibrates violently. The amplitude increases several fold. Okay, so normally when you're designing vibrations and where there are external systems, external forces acting, so we'll try to avoid the resonance conditions. Okay, so resonance is an avoidable conditions. So generally, you might have done your basic military training, right? BMT. So normally the soldiers are not allowed to march on bridges. So when you're crossing on a bridge, so you cannot march. So when you march, you create a similar frequency, and that frequency may, if accidentally matches with the natural frequency of the bridge, so the bridge may collapse. So if it is a normal wooden bridge, then it may collapse because it vibrates. All right. So resonance is, you should never forget this, guys. Please note down. So resonance is a condition in which the natural frequency of the system equals to the external frequency of the system or external frequency of the force. And omega is omega n. All right. So now in this case, what we need to calculate, we need to find out the response y of the system. Okay. So we can write down the spring force F as K into the displacement K into delta. Okay. So initial force, because this delta is varying with respect to the given equation 10 sine 80. So the initial force F naught, you can write it as K O delta naught. So delta naught is equivalent to F naught over K. So delta naught is the initial displacement. All right, so now we can write okay, so we know that the steady state amplitude for this from the response we can write the YP maximum. So this is the particular solution. So particular solution refers to the steady state. Okay, so the amplitude under steady state conditions, we can write F naught over K into 1 minus omega over omega n whole square. Okay, so you can replace the F naught with K into delta naught. Okay, so the particular solution you can, the complete solution response you can write like this. Okay, so here this P refers to, it is a typo, so you can write omega n. Okay, so this is the response given. Delta is delta naught into sine omega t. So where delta naught is F10. Okay, sine omega t is 80, so that means omega is equal to 8 radians per second. Okay, so the magnitude of the displacement is 10 mm. So we can write the natural frequency for the given system is square root of K over M. So K, there are 4 springs, so the total stiffness is 4 into 800. So mass of the system is given 20. So therefore, the natural frequency of the system is 12.6 radians per second. So this is the external frequency of the displacement, omega. So that is the frequency of the platform with which it is oscillating. So therefore, you can substitute these values to get replacing K delta naught with F naught. Okay, so the amplitude of the vibration flow, you can calculate YP maximum, okay, from this expression. So delta naught is 10, 1 minus omega over omega n. So once you calculate this, then you know the maximum displacement with which the platform oscillates. So that is 16.7 mm. Then okay, so to get the complete solution, so we know the YA sine omega nt plus b cos omega nt plus yp into sine omega t. Okay, so this is the solution, right? Y. So if you refer from where you're getting this equation, you're getting this equation from here. So a sine omega nt plus b cos omega nt. So this is replaced with yp, okay, sine omega t. So now we are writing the same thing here. So a sine omega n is the natural frequency, so which we calculated here. So that is 12.6. Okay. So b cos omega nt. So yp is the maximum displacement which we calculated, 16.7. Then sine omega t. Omega is the external frequency, 8. Okay. So this is the solution for the displacement. Now we need to find out here what are the unknowns. We do not know A and B. So we need to calculate A and B. Now to calculate this, we take the derivative of the displacement. So therefore we get velocity. Okay. So if you take the derivative of this, so y dot is the dy over dt. Okay, so if you take the derivative of a sine 12.6t, so you this 12.6 you need to multiply a omega cos omega t. Okay, so similarly here b my okay cos differentiation becomes negative, so it comes with a negative sign, minus b omega, that is 12.6 into sine omega t. So similarly here you multiply this, you take the derivative, so 16.7 into 8, so that gives you 133, and sine omega t becomes cos omega t. So 16.7 into 8, then cos 8t. So 16.7 multiplied by 8, you will get 133.3. So this is the velocity. Okay. Now from the description of the problem, so when the displacement is 0, okay, you are given that the velocity is also 0, and when the time is 0. So I'll just show you the description. Okay, so determine the vertical displacement of the platform. Okay. So you can read here, initially the platform is, okay, so initially the platform is at rest when the floor is subjected to a displacement. So initially means when the time is 0. So when the time is 0, the displacement is 0. So when the displacement is 0, the velocity is also 0. So therefore we are applying the initial conditions here. Okay, so we know that when the time is 0, the displacement is 0, and also the velocity is 0. So now we apply in the first equation. So we take this as equation 1, and we take this as equation 2. And equation 1, we replace time t is equal to 0, y is equal to 0. So when time t is equal to 0, so y is equal to 0. So here y is 0. So when sine 0 is 0, so the whole term becomes 0. So b cos omega t, when t is 0, this becomes cos 0. So cos 0 is 1. Okay, so b into 1. So you will have b. Then here sine 0 becomes 0, therefore the whole thing becomes 0. So from the first equation, we can say that the constant b is equal to 0. Now from equation 2, we know velocity is 0 when time is 0. So y dot is 0 when time is 0. So cos 0 is 1. So 1 into 12.6. So you get 12.6a. Okay, negative B, this sign 0 becomes 0. Okay, so here the T is missing, so you need to add T here. So when T is 0, this becomes sine 0 and it will be 0. Again here cos 0 is 1, so this will be 133. So once you solve this expression, you will get A is equal to negative 10.6. All right, so now you substitute back A and B values in equation 1. So substituting the values A and B in equation 1. So now you can write the complete response of the system like this. Okay, so here we know everything. All the values are known. So we know as time varies, the oscillation or the displacement of the system also varies. So y is a function of time t. So this is the response of the. So next part is you need to calculate when resonance will occur. So resonance will occur when the frequencies, natural frequency becomes external frequency. So we know omega n is equal to 12.6, right? So when this is equivalent to 12.6, so that means when the external frequency also equal to 12.6, the resonance will take place. Okay, so resonance occurs when omega n is equal to 12.6. All right, so this is an example for the damped and forced vibration. Any questions on this? Let me know if you have any doubts or any questions on the example, guys. How about others? Only Di Cheng is responding. Okay, Indre and Michael also says, okay, how about others? I'm just counting how many of you will respond out of 25. So far, only 3. Okay, 4. Oh, Heva is still digesting, understand. All right. Okay, so this is how we can study the response. You need to understand what is meant by the equation of motion of a system, and what is the free response, okay, free vibration and forced vibration. When we are dealing with forced vibration, then there will be 2 solutions for the response. One solution comes when we equate the right-hand side 0. So that is the response for free vibration. So that is the complementary function. Okay, then when we consider the right-hand side as the given external force function, and when you solve that, you will get the particular integral. So the total solution y consists of the complementary solution plus the particular solution. So for forced vibrations, you should know that the y, the complete response is the response due to the free vibration yc, which is the complementary solution, then the response due to the steady state or the external force yp. YC we have already done for damped free vibrations. Okay, YP is an additional component for the forced vibration. All right. So I clear this, then we move on to the next category. So the next category means now we include the damper also. So now we study the response of a system when there is external force acting and you are dealing with a damped system. So that means our system has M, K, and C. So we are dealing with a system with mass, stiffness, and a damper. Okay. So now we are going to study the response of a damped system under a harmonic force. Means when the system is subjected to external force. And the external force is, we consider the external force as an harmonic force. Okay, so now you can see here the force is, the system is subjected to an external force. So the difference between what we discussed just now and proceeding now is, so now we are also having a damper. So we are dealing with the damped vibration with external force. So now the first part is we draw the free body diagram. So now you can visualize the free body diagram. So the force is acting vertically downwards. Okay, so the spring force is K into X. So the damping force is C into X dot. So the damping force is C into X dot. So this is C into velocity X dot. Okay, so spring force is simply K into X. Okay, external force. So we write the equation of motion here. So by just writing the net force acting on the system is mass into acceleration. So this is the net force, mass into acceleration. So now the downward force, we take it as positive, F naught sine omega t. Then the spring force and the damping force both are negative. So we can write negative C X dot. X dot is velocity, CV, minus Kx. So minus Kx is the spring force. So we can write the expression like this. Then rearranging this, so we can write the equation of motion like this. Mx double dot plus Cx dot plus Kx is equal to the external force, F naught sine omega t. So here also you can see that F naught sine omega t is the forcing function or the external force. So external force, what is the frequency of the external force, guys? So can you tell me the frequency of the external force? Yeah, so omega is the, yeah, that's correct, Michael. So omega is the external force. So omega n is the natural frequency. Okay, so omega is the external frequency, force frequency. Okay, so omega n we can always write K by M. So when you are dealing with a spring force and a mass, okay, and omega is the external force frequency, and omega d is the natural damped natural frequency. Okay. So now this equation will have two solutions. Okay, this is the second order differential, non-homogeneous differential equation. Okay, x double dot is the second derivative, x dot is the first derivative, x is the function. So this second order differential equation is non-homogeneous because the right hand side is not zero. So right hand side is a function in sine. Okay, so there will be two solutions for this. One is the complementary solution xc. The other one is the particular solution. So now the particular solution depends on the external force function. Okay, so xc is, we know what is the complementary function. We have already solved the complementary function response for this. So considering the right hand side 0. Okay, so in the last session we have done that. So for a damped free vibration, what is the response? So at the beginning of the session also, I have written how to write the equation of motion. So that is your xc, the complementary function. So now we need to solve the particular solution, that is xp. All right. So xc is called the complementary solution. So which we already know because we have solved this equation when the right hand side is 0. We know the response of the system. So this is under damped free vibration. So now what we are doing? So we are doing damped and forced vibration. So therefore our solution will have the first part of the solution is the complementary solution. We take it when considering the right hand side of the differential equation as 0. Okay, so the next thing is we need to find out this xp, so which is the particular solution. So to solve this, then we need to assume based on the force function what will be the form of particular solution. Okay, the complementary solution is governed by initial conditions. That means when the time is 0, so what is the displacement of the system? What is the velocity of the system? So if you know those two things, you know the initial conditions. So the steady state response, this is the term which occasionally we use. So that means this refers to the particular solution. So under forcing conditions, how the system behaves. All right. So now we choose the particular solution in this form. Okay. So the choice of the particular solution always depends on the force function. So depending on the force function, we choose what type of particular solution can exist. So in this case, there are two constants, A and B. Okay, so you can solve this A and B. Okay, so take XP in this format. So you can always ask me why we should take like this. Okay, so this is one way of doing things. At the beginning of the session, I told you x can be expressed using both sine term and cosine term. X can be expressed by using both the sine and the phase of the. So in this solution, we are not considering the phase. Okay, so if we take the particular solution like this, then find out what is the first derivative of this xp dot. Okay, then find out what is the second derivative of this xp double dot. So that means this is the displacement. You are taking velocity and acceleration. So now these two things you substitute back into the equation. So what is the equation? So this is the equation. Mx double dot plus c x dot plus kx is equal to not 0, but or we can write f naught sine omega t. Okay. So once you substitute x dot p, x double dot p in the equation, so you will get this expression. Okay, so if xp is like this, x dot p will be a omega cos omega t. Then here minus b omega sine omega t. That will be x dot p. So you can see that portion here. Okay, so just substitute back into the given equations x dot p, x double dot p, xp, you will get this. So you are equating with f naught sine omega t. Okay, so if you equate the coefficient both sides, okay, the first part f naught, okay, you can write with the coefficients, okay, the whole thing. Then the second part you can equate with because this one has no constant, no cos omega t term, so we can equate this with 0. So you can solve these two equations mathematically, and you can find out the constant A like this and the constant B like this. So I'll not go into the mathematical part, and you'll not be asked to derive this in exams. Okay, so if you take any textbooks or any materials, so these derivations are shown. Okay, so just by choosing the particular solution like this and taking the first derivative, second derivatives, and substituting back into the given equation, differential equation, then we can simplify and we can solve for the two constants. So A and B can be solved like this. All right. So once you substitute back A and B in this, then that will be your particular solution. So once you substitute back A and B, you will get the solution. As I said, you can also choose the particular solution uh, with only a magnitude and with a phase like this. Okay, so you can also find out this XP in this case. Okay, and now where X, capital X is the amplitude of oscillation. Okay, so phi is the phase of the displacement. Okay, so phi is the phase of the displacement. So you can write expressions for both X and phi. So based on the solving the particular integral. Okay, so now solving the, okay, you can take x dot, x double dot, and substitute back into the equations just like the previous way. You can, this is an important expression, guys, you may note down, and this is an important expression for the phase. Okay, so this is the particular response we are choosing as x. Okay, I'll just show you this one, the particular response xp. So we are taking xp as magnitude x into sine omega t minus phi. So this is the particular response. Okay, so from there you can write down x is equal to f naught over the square root of k minus m omega square plus c omega square. And the phase can be written like this: tan inverse of c omega minus k m omega square. You can also write, please note down, let me just check it is there or not. Okay. So you can also write x, please note down. So this is one way of writing. So you can also write this as f naught over k Okay, this is a slightly a simple format. Square root of 1 minus r square whole square plus 2 eta. Eta is the damping ratio, R whole square. So we can also write the amplitude as shown here. So I wish all of you to note down this. So the same equation you can simplify and you can also write in this format. Okay, F naught over K over square root of 1 minus R square whole square plus 2 eta R whole square. So where R is equal to omega over omega n, the ratio of the frequencies. Okay, so you can also write the frequency phi. Okay, so this frequency phi can be written as okay, I write phi is equal to so you can write this as tan inverse of so you can write it as 2 eta R over 1 minus R square whole square. All right, so this will be your phase. So both equations are same, identically equal. Only thing is, so in this equation, you don't have the damping ratio, eta. So we are writing now the phase phi is equal to, so by this expression, by writing the damping ratio, eta. Okay. So guys, don't get confused. I'm just telling you how you can write the magnitude of the vibration in a different format like this. So similarly, the phase in a different format like this. All right, any questions? Okay, if you have no questions, then I move on. So here, now from the previous expression, so from this equation, okay, so we can write the ratio of x. So focus on this equation. So the ratio of x over f naught over k. So that means, so the k will go up, x k over f naught. So that one you can write it as 1 over the whole thing. So you can also write this as 1 over square root of 1 minus r square whole square plus 2 eta r whole square. Okay, so this equation we replace omega over omega n with r. Okay, so because omega over omega n is just a ratio of the two frequencies. Then similarly, you can write here 2 eta r over 1 minus r square. Okay, so this xk over f naught is known as the magnification factor. Okay, so then this magnification factor implies so the amplitude of the steady vibration over static deflection. So in other words, how the amplitude of the vibration is enhancing or magnifying. So the magnification factor you can calculate from this. So x represents the amplitude of the steady vibration, then over static deflection. So F naught over K is the static deflection. So this equation indicates the amplitude ratio is xk over F naught, and the phase is phi. Okay, so this is we are discussing the response of the damped forced vibration. The system is damped MKC. Okay, they are subjected to an external force. So we are dealing with a forced and damped vibration. Okay, so here we got the magnification. We defined the magnification factor, and we got the expression for the magnification factor, and also we got the expression for the phase phi. Okay, so we know the ratio omega over omega n, we call it as the frequency ratio R. So eta is the damping factor. So now we can see how the system behaves, the relationship between omega and omega n. Okay, so this you need to observe. Okay, so on the x-axis we are dealing with the frequency ratio R, omega over omega n, and on the y-axis you have the amplitude ratio. So a plot between the frequency ratio and amplitude ratio. Okay, so we just focus first on this. So you can see frequency ratio versus amplitude ratio. Okay, when R is equal to 1, when the frequency ratio is 1, so you can see here 1. Okay, so for different damping ratios, so for different damping ratio 0.1, 0.3, 0.4. So irrespective of the damping ratios, you can see the amplitude ratio is maximum when omega is equivalent to omega n. So that is where the resonance is taking place. When omega over omega n is equal to 1 means, so this is the resonance conditions. So omega becomes omega n. So omega is omega n means the resonance is happening. So during resonance, the amplitude ratio, okay, becomes maximum. Okay, so resonance conditions implies that two frequencies equals, and in which the amplitude of the vibration becomes maximum. Okay, so our job is to ensure that the system does not exposed to resonance conditions. Okay, now this figure basically tells you the relationship between the frequency ratio R and the phase angle. Okay, so irrespective of this, you can see when the ratio is 1, so the phase angle becomes 90 degrees. Okay, so the phase becomes 90 degrees when the amplitude frequency ratio becomes 1 or under resonance conditions. All right, so guys, those who are online, would you like to have a break, or you want to have a break at 8:30? How about you? All right, so I'll just continue with the two examples, then we'll have a break. Okay, so I'll continue. Let us let us go through with this. The weight is 50 newtons, is suspended from a spring stiffness. Okay, so weight is mg. Okay, the stiffness is 4,000 Newton per meter. This is subjected to a harmonic force of amplitude 60 newtons. So this 60 newtons refers to F naught, let us say. So this refers to F naught, external force. And frequency 6 Hertz. So here frequency is F. So F is equal to 6. Then omega will be. So what is the circular or radial frequency? So guys, calculate omega and let me know. So omega, we'll write it as 2 pi f. Okay, so under these conditions, so we know the spring constant, we know the weight of, that means we know the mass of the system, we know the force acting on the system. Okay, there is no damping here, there is no damper here. So the system is damped free, without damper, force vibration. So the external force amplitude is 60 newtons. So the external force magnitude. And the frequency is 6 Hertz. That means omega will be 2 pi f. Now, under these conditions, you're asked to find the extension of the spring due to the suspended weight, then the static displacement of the spring due to the maximum applied force. So you need to find the response of the system. And you need to find the amplitude of forced motion of the weight. Okay, we need to find out the amplitude of the forced motion. So these three things, it's quite simple, of course. The first one is the displacement of the spring. Okay, so this is force over spring constant, right? We know that F is equal to Kx. Okay, so X is equal to F over K. So here the force is the gravitational force mg, so which is 50 newtons. Okay, K is the spring constant. So the static deflection of the spring is 50 over 4,000. So you get 0.0125. So this is the deflection of the spring under its weight. So the extension of the spring due to the weight. Okay. So then the static deflection is due to the external force, which the magnitude of the external force is 60 newtons over spring constant. Okay, so that means the static deflection of the spring under the force is, okay, so 0.015 meters. So this is under the weight. So this is under the external force. So then natural frequency, you can calculate square root of K by M. Okay. So here K, you can replace K with F into X, mgx. So basically this is mg over the weight. Sorry, K into G over weight. So if under root, so you calculate this, you get the natural frequency of the system as 28.0143 radians per second. Okay, the external frequency is given 6 hertz, so convert into radial frequency, multiply with 2 pi. So if you multiply with 2 pi, you get about 37.7, let us say. Okay, so then we can write the amplitude of the vibration, x. Okay, so x can be written as static deflection over 1 over 1 minus r square. So if you do this, you will get about 0.0185 meters. Okay, so this is a straightforward, simple calculation. In this case, you don't have the damper, so you're only dealing with the weight and the spring system. Okay, the next one, I think we have the damper also. Okay, so here you are asked to consider a spring mass system. Okay, only K is given, mass is given. Okay, subjected to a harmonic force. Here the force is given as 400 cos 10 t. So omega will be 10. And F naught is 400. Okay, so the initial conditions are given. Find and plot the total response of the system under the following initial conditions. So the initial conditions means when the displacement is 0.1 meter, okay, the velocity is 0. Okay, when the displacement is 0, the velocity is 10 meter per second. Okay, when the displacement is 0.1, then the velocity, okay, also 10 meter per second. So under different conditions are given. So A is one condition, B is another condition, C is another condition. So first thing, K and M is given. So your first calculation will be the natural frequency of the system. So K, these are the values given. So K is given 400, M is given. So the function F is given as 400 cos 10 t. Okay, so F naught is 400, omega is 10. So you can calculate the natural frequency of the system. Okay, so omega n is square root of K by M. So K is 4000, M is 10. So that will be 400, and the square root of 400, you will get 20 radians per second. So we know the external frequency is 10, force frequency is 10. So you can calculate omega over omega n ratio. Okay, so the ratio is 0.5. So we know R is 0.5, then you will be able to write the response of the system. Okay, you can, okay, so this is the response of the system, the whole. Okay, this one you can copy from the previous theoretical examples. Okay, from the generic case, you can write down this. Okay, so this is simply A cos omega t plus B sin omega t plus this is the particular solution. So complementary solution is this. This is the particular solution. So now you apply the initial conditions. So the first condition is when displacement is 0.1, the velocity is 0. So that means when time t is 0, the displacement is 0.1. So replace xt with 0.1. Okay. Then here replace t with 0 and simplify. So once you do this, I think you will get the displacement as, okay. The response is just shown like this. So this is the response. So you just calculate putting t is equal to 0, all those values. So no, here the displacement is just given, initial displacement is 0.1. Okay, so this is calculated as 0.1 minus the whole thing. So finally you will get, okay, I need to take out this 0.1. It is shown here. So it is taken here. Okay, so just substitute instead of x 0.1 and okay, whatever the quantities, you just include omega square, you can replace with whatever the value, that is 0.5 square. Okay, just simplify this, then you can write the response as shown here. Then the second part of the thing, the conditions are changing. In this case, the initial displacement is 0, then the velocity is 10. So the same response equation, just by substituting wherever you have the displacement with 0 and velocity 10. So I think the response will be like this. Okay, the third condition, so you have a different condition for part C. Okay, so these are the two conditions. So you just replace from this, okay, the displacement as 0.1, the velocity as 10. Okay, the omega we know already, the ratio of frequencies. So the final response will be like this. All right, so any question, guys, so far? So we have seen for a forced vibration, when we are dealing with a simple mass and spring system, we got the response. Okay, we know how to solve the system when the system is subjected to an external force. Again, we have taken a system with a damper, okay, then subjected to external force. Then we have seen how to get the response for the system. All right, I'll stop here. We can have a break. Okay, so now the time is nearing 8:30. So let us meet at so 8:50. Is that okay, guys? All right, so I'll see you again at 8:50. Hi guys, hope you're all back. Shall we start? Okay, how about others? So some more responses. All right. Okay, guys, then we'll start. Now, this is your fifth assignment question. As you know, in the last session, we discussed the first four questions. Okay, so now let us go through the remaining four questions. Okay, so let us go through this. A boy riding a bicycle can be modeled as a spring mass damper system. So you are basically dealing with a MKC. Okay, so instead of mass, you have the weight. So if you know weight, you also know mass. The spring constant is given, and also the damping constant C is given. So C, K, and you have mg. So due to the different settings of the concrete blocks on the road, the level surface decreases suddenly as indicated in the figure. So you can see as the here when the time is 0 at point A, the vertical displacement of the block is 5 cm. Okay, the level of the surface decreases suddenly as indicated here. So you're equating the uh, riding of the bicycle by the boy as the mass spring and damper system. So at time 0 at A, the vertical displacement is 5 cm. Assume that the bicycle is free of vertical vibration before encountering the step change on the road surface. So before that, the vertical displacement is 0. So you're asked to determine the vertical displacement of the boy caused by the step change in the road surface. So what will be the vertical displacement when he is subjected to a vertical displacement of 5 cm when the time t is equal to 0? So how we are going to do this? So basically we need to find the response of the system. Okay, so to get the response of the system, the first based on the calculations data given, so we can calculate the natural frequency of the system. Okay, so what is given? Okay, assume that the boy and the bicycle fall as rigid, consider as a rigid body. Rigid body means no displacement. 5 cm at point A. So thus the equivalent mass will be, so basically you can say that the x naught is 5 cm. So you can write it as 0.05 meters at point A. So at point A, x naught is 0.05. So what will be the velocity at point A? Guys, anyone, what will be the velocity at point A? Yes, correct, Richeng. So the velocity will be 0 because displacement is constant, so velocity is 0. So you can calculate the natural frequency of the system. So can you calculate and let me know your answer? So equivalent spring constant given is 50,000. So which will be 50,000 over the mass equivalent. So the weight is given 800 newtons. So you can take 800 over 9.81. I need your answer for this. Calculate and let me know the natural frequency of the system.
24.76.
Say again.
24.76.
How about guys online? What is your answer? I need to get at least 4-5 answers. 2.524 is not correct. Yeah, that's correct, Andrew, but you need to give me the unit also.
18 per second.
Yep. So this will be 24.76 radians per second. So this will be the natural frequency of the boy and bike system. So if you know the natural frequency of the system, then you can calculate the critical damping constant Cc. So calculate the critical damping constant Cc. So 2m omega n. So 2 times. So mass is 800 over 9.81. Omega n, you can take it as 24.76. So I need few answers from you.
388,632.96. 388,632. Oh, okay. 4038.
Hmm?
4038.33.
That's correct, Daryl and Michael. So you get about 4038. So what are the value you get? So 33, yeah? The unit. So you need to always give a unit for whatever the number. If the quantity has no units, you can leave it as it is. Otherwise, you must specify the units, Newton second per meter. So it is simple to memorize. So force spring constant is Newton per meter. So damping constant is Newton second per meter. All right, once you know damping constant and uh, you can now calculate damping ratio. So what will be the damping ratio, eta? So we can write damping ratio eta is equal to C over Cc. So damping constant over critical damping constant. So we got critical damping constant and also damping constant is given. So damping constant is given as 1000. Then you got the critical damping constant. So what is your damping ratio? Anyone?
0.2476.
So I need few answers from online guys. 0.25, you have zero.
Yes.
Okay. Uh, 0.25 is acceptable, but yeah, 0.247 is more precise. Okay. So here, because it is a ratio, no units are required. So once you know this, then you can calculate the damping constant, uh, damped natural frequency omega d. So calculate omega d. So let me know your answer for the damped natural frequency.
24.
That's correct, Michael. How about others? So probably you can round it off to 23.99 units. Radians per second. All right, so we know omega d is 23.99 radians per second. So next, the response of the system, we know xt can be written as capital X. The response of the system can be written like this. So I clear the calculations. Okay, so the response of the system is x, which is depends on the time, the displacement. Capital X is the magnitude. So eta is the damping constant ratio. Omega n is the natural frequency. Omega d. So you know everything here. So you need to know what is the capital X, the amplitude. So the amplitude X can be given as okay. So x naught square, you guys may note down this. X naught square plus so this is the velocity x naught dot square k plus eta, the damping ratio omega n x naught over omega d square, okay, under root. So the whole thing under square root. So you know everything. So calculate this. So this is x naught dot velocity square. So as you know, this x naught dot is 0,
0.05.
velocity.
Of course.
X naught is 0.05, correct. So guys, I'll wait for your answer. I think just okay, just a minor correction. So this x dot, there's no square here. Uh, so just hold on, guys. I think there's, so the whole thing 1 by omega d. So you need to take x naught dot plus eta omega n x naught, okay, whole square over omega d. So this is whole square. Is that clear, Eva? Uh, Let me write like again. So I clear. Darrell, that's correct. So you can check your equation once again. So what's your answer?
0.0518.
So probably you'll get about 0.0516 unit meters. So this is the magnitude of the vibration. then you need to calculate the phase. So what will be the phase? So phase you can calculate as tan inverse of okay. So x naught omega d over x naught dot plus eta omega n x naught. So guys, calculate the phase also. So any answer for the phase? Second. Any answer from online? 75.7 degrees. Yeah. So you can so now you know the magnitude and also you know the phase. So therefore you can use this expression and you can write the response of the system x, which is the displacement. That means when the boy is riding over the bike, so how his vibration vertical displacement varies with respect to time due to the step which is having a vertical displacement of 0.5 meters. Okay, so just replace the value of x, include everything and write down your final answer. Okay, I'm not reproducing this, so I expect all of you to write down the final response, incorporating the values of the magnitude capital X, the damping ratio eta, the natural frequency, then there are omega d, the damped natural frequency, and the phi. So incorporate all the numerical values and write down the system. So except time t, so all other things you know. So that means you can calculate how the response varies with respect to time t. Is that clear, guys? Any questions? So you need to work out this like this, write step by step, and wherever required, provide explanation. Okay, if you miss the units or if you don't write all the steps, you may lose some marks. All right, so let me know any questions quickly. What is the E? Where is E? Where did I write E? Daryl, where did I write E?
XE. XE.
The response, X is
XE.
this one,
Uh,
exponential. E refers to the exponential power. So E is the value of E will be about 2.71 something. So this is the exponential. So exponential is the mathematical constant. So it is 2.718. So it's a constant. So exponential is an important constant which we'll be encountering many a times. Okay, so this value comes as a value of a series of values 1 over 1 plus x whole square. Okay, it's the inverse logarithm, natural log. So natural logarithms are based on exponential value 2.718. All right, any other questions? So if not, we can move on to the next. All right, so then we move on to the next question. Okay, so this is a question wherein there is an angular displacement. Okay, the two springs are connected, so it's connected with the there's a rotational system. So there is a pin joint here. There's a bar. The bar is subjected to two springs. Okay, so there's a torque applied on the system. Okay, so the external torque acting on the system is here. Okay, so the value of this is m naught is given. So the moment acting 100 Newton meters. Omega is given 100 rotations per minute. So you need to convert the rotations into radians. All right. So K is given. So the L value is given as 1 meter. The mass is given 10 kilograms. Okay. So you have to, the rotational inertia of the rigid body above the hinge O can be given. So the mass moment of inertia is given as 7 ml square over 48. So this is the mass moment of inertia for this rigid bar is given as 7 ml square over 48. So if it is given, it's all right. Otherwise, we can also calculate this. For the rod, inertia is half ml square. So we can apply the parallel axis theorem and we can find this value. But the good thing is for this problem, the value is given to you. So 7 ml square over 48 is the mass moment of inertia. So for this problem, we have to derive an equation of motion, and then find the steady state response. So two aspects: derive the equation of motion and then find the steady state response. So you can see here the system has only M and K. Okay, and how do you get the response of the system? So here there is an external moment is acting. So M naught cos omega t. Okay, the inertia through the hinge is given. Okay, so what is the net torque acting on the system? So generally we apply the Newton's law as the net force acting on the system is equivalent to mass times acceleration. Okay, so now in this case, what is the net torque acting on the system? So the net torque acting on the system, so you can write it as I into alpha. So this is something like your F is equal to M into A, mass into acceleration. So the torque, which is nothing but the rotational force, okay, or moment of force, which is I, okay, if you want, you can write I naught, because you are referring this mass moment of inertia with respect to the hinge O here. Okay, so this is the net torque acting on the system. So this torque is subject, you can also equate with the force multiplied by the perpendicular distance. So what are the forces acting here? Okay, so there is a spring force here. Okay, and so there is a spring force here. And there is a moment here. So this we can write the net torque acting on the system. Okay, I replace angular acceleration alpha with theta double dot. So we can write I naught theta double dot. Okay, so this is equivalent to, okay, so the movement due to the spring force. So what is the movement due to the spring force? So spring force, you can write K into X, right? K into X. So which is, what is X in this case? So you know that there's a relationship between, this is L over 4, okay? Theta is the angular displacement. So theta is the angular displacement. Okay, X is the linear displacement. So you can write X is equal to, okay, R into theta. So what is R? In this case, R is L by 4. Okay, the linear displacement, you can write it as R times angular displacement, L by 4 into theta. So K into X is the spring force. So what is the movement due to the spring force? So the movement is force multiplied by the perpendicular distance. So you can write K X. So instead of X, we write L by 4 into theta. Okay. So what is the movement developed due to this? The movement developed due to this is multiplied by the perpendicular distance, L by 4. Okay. So spring force multiplied by the perpendicular distance, L by 4. So this is the movement due to the first spring force. Then there is an external movement here. So you can write an external movement we write later. Then what is the movement due to this spring force? Movement due to this Fs. So we can write the same thing, K into X, that is the spring force. So for this X will be 3L by 4 into theta. Okay, so you can write minus again K into, okay, so here we write 3L by 4 into theta. So this is the spring force K into X. Then what is the movement due to this? The spring force multiplied by the perpendicular distance. So the perpendicular distance to the hinge is 3L by 4. Okay. So if you want to equate with this, then we need to add the torque acting on this. So the torque acting on this will be positive. So we can write m naught cos omega t. Okay. So this is all. We just apply the Newton's law for rotation. Okay. So the net torque acting on the system is I naught into theta double dot. So this net torque is equal into the sum of the moments acting on the system. So what are the moments acting on the system? So movement due to this spring force Fs. So Fs is K into L theta by 4. So this distance, perpendicular distance, is L by 4. So the moment due to the spring, first spring Fs is, this is negative K L theta by 4 into L by 4. Then similarly, the moment due to the next spring is minus K 3L by 4 into theta, then multiplied by 3L by 4. So then plus external torque acting on the system. So m naught cos omega t external. So these two things, now if you simplify this, you will get equation of motion. So this one becomes K L square theta by 16. So I can write I naught theta double dash is equal to, so negative K L square by 16 so into theta minus K, so 3L multiply 9L square over 16 theta. Okay, so plus m naught cos omega t. Okay, so We can write like this, right? So now you can see theta is common factor here. So this is negative k L square over 16. This is negative 9L square over 16. So combining these two things, okay, so 9 plus 1, 10, 10 over 16. So 10 over 16 means 5 by 8. So you can won't the KL square by 16 become positive? Yeah, you can do that, Michael. So you can now just, now both forces will be acting upwards, therefore both are negative initially. So you can write I naught theta double dot. So now you can bring this the other side. So negative KL square over 16, then minus 9 KL square over 16. So if you bring the other side, it becomes 5 by 8. So 9 plus 1 becomes 10. So 10 over 16 is 5 over 8. So 5 by 8, then KL square. So 5 by 8 KL square theta. Okay, so you can write it as m naught cos omega t. So this will be the equation of motion. All right, so the equation of motion is just bring these two negative things to the other side. So then write down. Okay, so theta double dot is the angular acceleration. So theta is the angular displacement. Okay, so I naught value is given, so which is 7 m L square over 48. So you can just calculate what will be this value, because you know mass L value is given. So therefore you can calculate the mass moment of inertia or the rotational inertia. So how much this J naught will be? So can someone give me the value for the moment of inertia? Uh, how much is it? Let someone from online can give the answer. So anyone calculated online, guys? What's the unit, Michael? So 1.458. Any unit? Second? Huh? Loudly. No. So mass is kilograms, right? So you can write kilograms. L is meter square. So kilogram meter square. All right. So you will know now once you incorporate this value. So this becomes the equation becomes 1.458 theta double dot. So then plus 5 by 8 k L square theta is equal to m naught cos omega t. So you need to get the response of the system. So how do you get the response of the system? Okay, so I clear this. Is that okay? I clear this calculation. Let me see. Yeah. So to solve this, the response of the system, we can write it as theta, which is instead of x, so we can write theta as a function of time t. So we can take this as theta into cos omega t. Okay, so here this theta is the magnitude. So you can substitute this equation, take the first derivative, take the second derivative, okay, solve this equation for theta. So then this theta can be given as, okay, the magnitude of the displacement. We can write it as m naught over 5 by, I'm giving you the final equation, 5 by 8 k L square minus I naught omega square. So this will be the theta value, that is the maximum angular displacement or amplitude of angular displacement. So you can calculate this value. So m naught is given the moment acting on the system. So m naught cos omega t is, okay, m naught is 100 Newton meters. So K stiffness constant, L is given 1 meter. I naught you calculated. So omega is the angular frequency. Yes, Hazan? Yes, you need to change RPM into radians per second. Omega need to be converted. How long is correct? The answer will be you get about 0.0334 radians. All right. So this is the working for this question. So you have to convert this omega 100 RPM into radians per second. So one rotation is 2 pi radians. So multiply with 2 pi. Then divide by 60, convert into meter rotations per minute, convert into rotations per second. All right. Any other questions, guys? All right. So if you have no other question, thanks, Michael. Then we move on to the next part. Okay. So let us look at this question. So this is a single cylinder reciprocating compressor on a spring support has the following data. So the mass of the engine is given 600 kilograms. Then the equivalent mass of the reciprocating parts is given 20 kilograms. The stroke of piston is given as 225 mm. Okay. So the static deflection of the spring is given due to the weight of the compressor is given 40 mm. So the ratio of consecutive amplitudes. So here, the ratio of consecutive amplitudes is given as 1.00 and 0.55. So once we have this, then you can calculate the logarithmic decrement. So you can write the logarithmic decrement. So we can write logarithmic decrement delta is equal to, so natural log of the ratio of the two successive amplitudes. So the first one is 1.00, so over 0.55. So if you calculate this, then you know the logarithmic decrement for this person, the response of the system. Any answer for the logarithmic decrement? Guys, any answer for the logarithmic decrement? 0.598. So this is just a number, so no units. So we can write 0.598. Okay. So the last sentence of the question says determine the amplitude of the compressor vibration at 320 RPM. So this is your omega. So convert this omega, the compressor vibration, into radians per second. So omega convert into radians per second. So that will be 320 into 2 pi over 60. So can someone tell me what will be the omega in radians per second? 33.51 radians per second. That's correct, Darren. Thank you. So this will be 33.5 radians per second. Okay. Now, this is a single cylinder reciprocating mass. So when a system is reciprocating, okay, so something like, so system is having a mass, okay, which is, okay, this is subjected to the normal force. So the normal force is equivalent to, so we can write the force due to the reciprocating mass is F naught, okay, M into A, acceleration. So for a rotating mass, the acceleration is, okay, we can write M R omega square. Okay, you might have studied this in, you must have done this in engineering dynamics. So mr omega square. You know what is omega? 33.5 radians per second. So you can calculate the reciprocating or the force acting on the reciprocating mass compressor. So here m is the equivalent mass of the reciprocating part. So this is your small m. So what is the R? R is your the stroke of half the stroke of piston length. Okay, so R will be 225 mm over 2. So that means convert into meters. So 0.225, half of the stroke length. So 0.225 over 2. Okay. So mass is 20 kilograms. R is 0.225 over 2. Omega is 33.5 radians. So calculate what is the force acting. So R is half of the stroke length. Any answer? If not, the force acting on the compressor, reciprocating compressor. Uh, 75.4 watt. Calculate again, Daryl, not correct. Because this 33.5 square itself is a big number. That's correct, Eva. So you get about 2,525 newtons. So you can round it off the figures. So this is the force acting on the system. Okay. So can you calculate the natural frequency of the system? Omega n is equal to K by M under root. So calculate what is the natural frequency of the system. Okay. So, we can replace this K with mg over delta. So that becomes, this becomes G over delta. So G is the acceleration due to gravity, delta is the static deflection. So static deflection is given as 40 mm. So 40 mm convert into meters. So you can calculate the natural frequency of the system, okay, which will be 9.81 over 0.04 under root. So here the system is subjected to gravitational force. So we replace K with mg over delta. So mm gets cancelled and you have the natural frequency as square root of g over delta. So how much you get natural frequency? So any number for the natural frequency? So Shafruddin is giving me 15.66. So unit? Yeah. So that's correct, Shafruddin. So 15.66 radians per second. All right. So now you got so many things. I move to the next page. I would like to okay. So we can continue. What are all the things we know? So we can calculate R. So R is the ratio of frequencies, omega over omega n. Okay, so we know logarithmic decrement delta. So delta, you got it as 0.598. So this one we can equate, consider the damping constant because this is a reciprocating mass. So we consider the damping constant, damping ratio is low. So we can equate this with 2 pi eta. Okay. So we can equate the logarithmic decrement delta with 2 pi into eta. So this one we can only apply for when eta, the damping ratio is small. So we consider in this case the damping ratio is small because the system is subjected to gravitational force. Okay, and yeah, so calculate the damping ratio eta. So you can calculate the ratio of the frequencies R, then you can calculate damping ratio. Okay, so then you can calculate what is x naught, the amplitude displacement. So x naught, you can write it as f naught over k. So how to calculate k? K is, so mg over, so the total mass of the system, the weight of the system, mg, over the deflection. So static deflection is given as 0.04. So the stiffness is weight over the displacement, force over displacement. So this is, m is the mass of the engine. So 600 kilograms, then multiplied by 9.81 over 0.04. Okay, so you will be able to calculate the stiffness constant K. So any answer for K? 147150 units. So it is stiffness constant, force over distance. So Newton per meter. Okay, so 147150 newtons per meter. Okay, so then you can calculate x naught. X naught is f naught over k. So f naught we already calculated, mr omega square. Okay, so then we know that to calculate amplitude x over x naught, we know the relationship. Okay, magnification factor. So the magnification factor can be written as 1 over 1 minus r square whole square plus 2 eta r whole square under root. Okay, so this is the magnification factor. So from this, you know, okay, so you know everything here except capital X. So calculate the amplitude of the vibration. So you can incorporate all the values, then you can calculate x, the amplitude of the vibration. So x naught also you can calculate because f naught over k. So you know f naught and you know k, therefore you know x naught, the initial deflection. So I'll wait for your answer for capital X, the amplitude, magnitude of the vibration.
Times 10 to the power of -3.
1.3.
1.3.
Huh?
1.33.
So guys, I'm waiting for your answer. Very close. Anyone to confirm the answer? So if you give the number, I can confirm your answer. Yeah, the answer is correct, Ichan. So you get around 0.0048 meters. All right, so you got the answer right. Any questions? So basically, we are dealing with reciprocating masses and only the mass and the stiffness constant. So here the external force is the force due to the reciprocating masses, R m omega square. Okay, so we can calculate the external force that is given because the system is subjected to a rotation of 320 RPM. Okay, so we can calculate the natural frequency of the system from the uh, weight of the system, mass of the system, engine, mass of the engine, and displacement. All right, so any other questions? Anyone? So your class test will have questions something similar. Okay. All right, so I'll move on to the last question. Okay, this is the question number 8. Okay, so we may just go through the question, what's given, then how to work out. So the mass is given 100 kilograms. The stiffness constant is given 10 kilonewton per meter. So 10 into 10 power 3. Okay. And it is pulled down 50 mm below. Okay. So the displacement is 50 mm or 0.05 meters. Its static equilibrium position and released. So there is a frictional resistance which is proportional to the velocity and is 360 newtons when the velocity is 1 meter per second. Okay. Here, the frictional resistance, which is proportional to velocity and is 360 so newtons. We know that the damping force acting is okay. We know it is c into velocity. So the force due to the damper is c into x dot or c into velocity. So damping constant c will be the damping force over the velocity. So x dot is the velocity. So based on the information given, we can calculate the damping constant. So the damping constant is now 360 newtons over velocity is 1 meter per second. So basically, the damping constant C is 360 newtons second per Newton second per meter. Okay, so we know mass, we know the stiffness constant, and now we could find out based on the description the damping constant C. Okay, so we know the C value. So that means we know mass, K, and C. So C we can say, we can write it as 360 Newton second per meters. Okay, so the displacement when it is pulled on to 50 mm meter and released, okay, so there is a vibration. So now you're asked to the first part, write down the equation of motion and find its solution. So that means you get the equation of motion and find the response of the system. So the second part is calculate the time which elapses and the distance which the body moves from the instant it is released until it is again at rest at the highest part of its travel. So you need to find out the time taken to reach the highest part of the travel. So two things we need to find out. So basically you are dealing with a MKC. So your system is something like this. So you are dealing with a stiffness constant, a damper, and a mass. So I just draw the damper like this. Then you have the mass here. Mass K and C. Okay, so this is pull down a displacement of 50 mm. Okay, so this is the scenario. For this scenario, we need to write down the equation of motion. So the equation of motion, we can I clear this. Okay, so we can write down the equation of motion for this. So the net force acting on the system, we can write it as mx double dot. Okay, so this one you can write it as minus c x double dot x dot c into velocity minus kx spring force. So you can combine this and you can write mx double dot plus cx dot okay plus kx is equal to 0. So the equation of motion you can write, we know m, we know c, we know k. So just put down the values, then you can calculate, you can get the equation of motion of the system. So that is the first part. Write down the equation of motion and find the solution. So find the solution means you need to find the response of the system. So x is, okay, write down. So I think I'll just briefly tell you what to do. Then you can complete this question. I'll not give you the complete solution so that you can work on your own. Okay. So need to calculate the natural frequency of the system. So first calculate the natural frequency of the system. Then calculate the damping ratio of the system, eta. Okay. So then you can calculate the damped natural frequency of the system. Okay, so that is omega n into square root of 1 minus eta square. So then you can write the response of the system x as, okay, so capital X into e power minus eta omega nt then you can write, sorry, so you can write sine omega dt plus phi. So this is the response of the system. So you can calculate the response of the system. So for this, the initial conditions are given. Okay. So the initial condition is that means the initial displacement is given. So the initial displacement is 0.05, 50 mm below, pull down. Okay, so based on this, try to calculate and complete both parts. All right, so just to differentiate among you, so let us see who can give me the perfect solution for all the questions. All right, so when you submit your assignments, make sure that you write clearly step by step. Okay, I want to see all the steps and all the calculations required. Then you can expect full marks. Otherwise, your marks will be slightly deducted. All right. So, any questions before we conclude the session? So I consider all the assignments were done. Then you are ready to submit your assignments. Okay, you know your due dates. All right. So, all right, guys. Any questions? So this question you can attempt on yourself. Complete this. So no one is responding. Hmm?
No, sir. No, sir.
No questions from your side. You guys can go. All right. So if you guys have no questions, then Eva is asking me, but for the mechanics solid assignment, will you go through the different milestone? Yes, we have, I think the next two sessions we have solid mechanics. So I'll be going through all the milestone questions, Eva. Nothing to worry on that. All right. Okay. Okay, then thank you all and good night and see you next time.